Hello, this is the second unit on the transformer. And this is a sort of cleaning up some odds and ends, important odds and ends. So this is a review. The transformer, there's a notion of a transformer layer. I'm representing it as 6 sublayers. The last unit, we did this self-attention layer in detail. Here's the graphical picture. The fundamental points is that the main innovation in the transformer is this self-attention layer. And I forgot to mention last time that there are 2 big advantages of the self-attention layer. One is that it's parallel, it executes in parallel, so we don't have to wait for an RNN to scan the sequence. So we can make the sequences very long, and if we've got enough parallel hardware, it's not slowing it down, right? We can just keep computing these layers, and each layer in log time up the layers. Time efficiency is one advantage. The second advantage is that because the self-attention is looking just as easily at the very beginning as anything that's close. It's looking very easily across all of time. And what that means is that the memory behavior is better. So for very long sequences, the attention mechanism has direct access to something that happened a long time ago. And that's the other big advantage of the self-attention layer over an RNN. Okay, so this is the picture. Self-attention, residual connection, normalization, feed forward in time, residual connection, normalization. And that's the transformer layer. Layer normalization. So the layer normalization was introduced after batch normalization, but before the transformer. So the basic idea here is that we're going to get away from averaging over the batch when we estimate the mean and variance. So we're just going to assume a layer. So the way this works in the transformer architecture is that we have layers of this shape, right? We've got time and neuron. And we're going to take the whole layer across both time and the neurons, and we're going to average over both of those to get an average neuron response, right? So this is an average neuron response across the whole layer and across all neurons in the layer. And we take the variance across all neurons at all positions. And then we do just what we did with batch normalization. We take the input layer and we subtract the mean, divide by the variance. And after we've subtracted by the mean and divided by the variance, we apply an affine transformation that is scaling, taking the result of this normalized layer minus the mean over the variance and multiplying it by an arbitrary constant and adding an arbitrary bias. And then pumping it through a rectified linear unit. So the normalization is typically done right before you apply a threshold function, an activation function. And this step is the same as batch normalization. Batch normalization also included this affine transformation after the normalization. But the advantage here is we're not averaging over the batch. So this algorithm is independent of batch size. It also means that at test time, the test time algorithm is the same as the training algorithm. There's no batch at test time, but it doesn't matter for this algorithm. Okay, the other thing that is in here is feed forward layers. So the feed forward layer, remember, is operating at each position independently. And it's just a 2-layer perceptron. So, so the 2-layer perceptron takes the input layer, this is the input layer, and just passes it through a set of linear threshold functions. Just it multiplies this layer by at each point in time. You're multiplying the vector at that point times a matrix and subtracting a bias term, and then you pump that through a ReLU. You get your first layer of your multi-layer perceptron. And then you take this as input and get a second layer of your multi-layer perceptron. The second layer is not put through an activation function, a threshold function, because we're about to pass this through a normalization which will then pump it through an activation function, a threshold function. So here's the picture of the transformer again. So these feed forwards are happening at each time point independently. Okay, this is an important odds and end. This is an important aspect of the transformer that I have not talked about. If we consider the input, now in a recurrent neural network, the input is just the sequence of word vectors, the sequence of, you have a sequence of words, you convert each word to a vector via a table, a matrix that assigns a vector to every word. And that sequence of word vectors is input to the first layer of the recurrent neural network, because the recurrent neural network wants vectors as inputs. In the self-attention layer, the attention is computed by looking at the query vector and the key vector of two positions. And those two vectors are computed from the vectors at those positions by a matrix multiplication. Without additional information, if we simply used the word vectors at every point, the order has been lost because the attention just depends on the vectors and not on the order, and not on where it appears. So if we do it naively, the whole network treats the input as a bag of words. There's no position, the sequence information is not used in the attention. So the solution to this, you clearly want to include the order of the words in the model, in the analysis of the sentence. So the solution to this is to make the first layer a concatenation of the word vector at that position. So the first layer at position T is a vector J, is a vector with dimension J. And we're going to take the word vector of the word at time T, and we're going to concatenate a position vector for the time T. So each time is associated with a position vector. And in the original transformer, the position vectors were handcrafted to be sort of, they used these cosines at different frequencies and made a vector out of cosines at different frequencies. But the modern architectures tend to train all of these. They train the word embeddings and the time embeddings as part of the parameter models. And there's more to say about that. It feels much more meaningful to me that when you compute an attention between T1 and T2, it's the distance, the difference between T1 and T2 that should be used as the position embedding, not any pair of absolute position embeddings. And some recent models have done that. Language modeling. Okay, so all I've described now, so far, is a way of taking these sequences of vectors and computing new sequences of vectors by stacking these transformer layers. How do we do language modeling? So what is language modeling? Language modeling means you take a sequence of words and you compute a probability distribution over the next word in an autoregressive language model. You're always computing the probability distribution over the next word one at a time. And the transformer is sort of looking at everything simultaneously. So if I've got a sequence of words and I want to train the transformer to compute a probability distribution over the next word, when you're computing the probability distribution over the next word, you should not be looking at the next word or any future words. You can't look into the future when you predict the probability of the next word. So the way you do that efficiently is when you compute this attention, if T2 is greater than T1, you force the attention to be 0. You mask it out, you blank it out. And that means that the attention, so a given word is paying attention only to itself in the past. And then when you compute the probability of a word given previous words, you can take a softmax over this, given the way you compute a probability distribution in an autoregressive model of the next word is to do a softmax over the possible next words of the embedding of that possible next word, inner product with a vector at that position. And we'll just take the top vector of the transformer to be the vector at that position. But but you're taking the vector at the position at the previous time step. And the vector at the position at the previous time step has not seen anything that's in the future of that. So this becomes a legitimate, this probability only depends on the words up to, but not including the word you're predicting. And that's just handled by forcing this masking. It's not exactly correct because in some sense, because when you're predicting the next word, each word in the past has only seen the words that were before it. And it would be legal that when you're predicting the next word to have the words in the past have access to all the words in the past in computing their vectors. But this is what's done. This is fast in practice. So when you do this, and you do your training, your language model training on an input of length t, you're just computing one transformer pass over that input of length t. And you're getting updates for all of the predictions in that block of text you're looking at. So this becomes very efficient for training language models. Machine translation. In the original paper, which was called Attention is All You Need, the application was machine translation. Now, machine translation is a conditional language model, right? You're taking an input sentence and the model produces a autoregressive model of the translation of that sentence, of the probability distribution over the translation of that sentence. So we can, if we have translation pairs, we can just take the pair with a special token in between them, the input and its translation. So if we're given training translation pairs, we just train the translation by predicting the translation words as a function, while using attention over the input. So we always have access to the whole input, but we use a language model training algorithm, which is blanking the future as we construct the probability distribution of the probability value over the translation that's given in the translation pair. I don't know if that was clear. We have a translation pair. We're training a language model. The language model is producing a probability distribution over the translation of the given input. We train that language model the same way we train any language model. It's just that it's not asked to predict the input. It's only asked to predict the output. Okay, now let's do something fun. So I want to remind you that the transformer was introduced in June of 2017, so a little over 3 years ago. So in those 3 years, it has pretty much completely replaced recurrent neural networks, LSTMs. So in June 2018, this is a year later, a year after the transformer appeared, this kind of shocking language model appeared. And what you can do with a language model, if you have a language model, you can give it a prompt, give it some initial sequence, and have the language model compute the probability of the next word from there on, right? So you give it some prompt and you ask it to continue by selecting words according to its language model probability. And there are tricks in making, you don't want to just sample. You can tune the temperature of that sampling and it tends to improve the output. Okay, so so there's this GPT-2 came from OpenAI. Continue from, so this is the prefix, this is the initial sequence they're giving to their language model, and their language model is going to generate text downstream from this sequence. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. Okay, now this is the computer. Sorry. This is the computer talking. Okay, they cheated a little bit. They did 10 tries and selected a good one. But anyway, now we have the computer. The scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this old phenomenon is finally solved. Dr. Jorge Perez, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when Perez and his friends were astonished to see the unicorn herd. While examining these bizarre creatures, the scientists discovered that the creatures also spoke some fairly regular English. I mean, remember that was in this prefix that occurred quite earlier from this, continuation. So it's remembering what it was told in its prefix. Perez stated, we can see, for example, that they have a common language, something like a dialect or dialectic. Dr. Perez believes that the unicorns may have originated in Argentina. Some believe that perhaps the creatures were created when a human and a unicorn met each other in a time before human civilization. However, Perez also pointed out that it is likely that the only way of knowing for sure if the unicorns are indeed descendants of a lost alien race is through DNA. When I saw this, I was shocked. This was another something else that led me to sort of believe in the Moore's law of AI. Okay, but now, July, just this past July, I'm sure you've heard of GPT-3. So GPT-3 is GPT-2's successor. Now we're dealing with 175 billion parameters. And in the last 6 months, say, people have really been emphasizing the number of parameters of the model rather than the size of the training data. The number of parameters of the model, the bigger models seem to do better, which is counter to a lot of machine learning stuff. And we'll get back to that later. More parameters, it's actually generalizes better. Okay, so this was 1.5, just to look at this is 1.5 billion parameters. This is 175 billion parameters, so it's like 2 orders of magnitude larger. And there was an undergraduate at Berkeley, I believe, who got access indirectly to this model and played the same game. So he's going to give it a prompt and the model's going to continue. And then he published that under his own name as a blog post. And this machine-generated blog post was ranked in the top 10 most retweeted or most commented on blog posts in the particular blog that he was working with. So the prompt is continue from, this is the prompt, feeling unproductive? Maybe you should stop overthinking. And I think I mistyped the beginning of this. In order to get something done, maybe we need to think less. Seems counterintuitive, but I believe sometimes our thoughts can get in the way of the creative process. We can work better at times when we tune out the external world and focus on what's in front of us. I've been thinking about this lately, so I thought it would be good to write an article about it. So what exactly does this mean? Well, for starters, let's start with some definitions. Definition 1, creative thinking is the act of using your mind to come up with ideas that are not already present in reality or that have never existed before. It is a form of mental activity that involves the use of logic and reason. Definition 2, overthinking. It is the act of trying to come up with ideas that have already been thought through by someone else. OT usually results in ideas that are impractical, impossible, or even stupid, and it continues. And I mean, it's got a lot of press, right? If a machine writes a blog post that a lot of people are liking, it gets a lot of press. One thing that's going on here is that this is like a self-help blog post, and these self-help blog posts don't require a lot of careful logical thinking or logical consistency. So this is a kind of sweet spot for language models. They don't have to really, well, there's a lot of question about to what extent they, quote, understand what they're generating, but they don't have to make it logically consistent. There aren't hard facts here that have to be respected as you go through the text. So this is a kind of blog post that we can get a plausible output for. There's this other thing that the GPT-3 paper was really about what's they called few-shot learning. So there's this really bizarre thing you can do. You can take, remember that you can give the model a prefix, some sequence of words, and ask it to continue. So they use that ability to, in a short prefix, tell the language model what problem they want it to solve. So, for example, consider machine translation. This is really kind of creepy. You give it a sequence of maybe 20 or 50 translation pairs. Say we have German, English, German, English, German, English. You give it, and you give it 20 of those or 50 of those. Then you give it a German sentence and you say continue. So it's continuing from a bunch of examples of German English. You're giving it just the German and asking it to continue, and it translates the German that you give it at the end. It's not, it's not competitive with any kind of machine translation, but it's kind of suggestive. It's kind of creepy. It's suggestive that it's learned to learn patterns, and it's learned to learn patterns and follow them from only a few examples. And it can do things like add 3-digit arithmetic. It can add 3-digit numbers. You give it examples of, X, Y, X plus Y, where those are 3-digit numbers. You give it a bunch of those and ask it to add X and Y, and it'll give you the sum. You can also unscramble words. You take a word and you scramble with letters and give it a bunch of unscramblings, ask it to unscramble, and it will unscramble. A very recent paper, just a few weeks ago, remember that GPT-3 is 175 billion parameters. People are really decided to push on that. There's something called G-Shard, which is up to 500 billion parameters, and teraparameter models are happening. So what's interesting about this paper that appeared just a few weeks ago, maybe a month ago, is that it showed that this escalation in the number of parameters appears not to be necessary. So this is a paper that has 223 million parameters. So this is approximately 3 orders of magnitude smaller, 3 orders of magnitude smaller than GPT-3. And they take this model, 223 million parameter model, and they demonstrate that you can get the same effectiveness of this few shot learning using other tricks, using something called distillation. And hopefully we'll get a chance to talk about distillation. Distillation is when you train, you train one model, and then you train another model to replicate the first model. And it's typically used when you train a big model and you want a small model that has the same performance. You treat the big model as a teacher and the little model as a student. And it's been shown that you can get little models that perform well when you train a big model and distill it, but it doesn't work to try to train the small model directly, even though, of course, the small model has in its parameter space the ability to do well because it can learn from the big model. So that's a whole area of deep learning, is distillation. But using distillation techniques and something called pattern exploitive training, they demonstrated that this model with 3 orders of magnitude fewer parameters could do the same kind of few shot learning that GPT-3 could do. And this was just 3 or 4 weeks ago. So it's going to be fascinating to see where this goes. All right, thank you.